Here we are, section 4.4, the last section of the semester. Congratulations for making it this far. I hope that you can kind of breathe a sigh of relief at the end and feel like you've actually learned some calculus and you've made it through what I think has been a pretty challenging semester. 4.4 is called the indefinite integral and the net change theorem. And what we're going to do is we're just going to teach you just a little bit of notation, and that is we know this integral. If we do the integral from a to b, we take the antiderivative, where f here is the antiderivative. So f is the antiderivative. Well, what we're going to do is we're going to develop a notation, which is just this notation right here, without the a and the b on it. And that, if we write this notation down, we're just going to write down the function that we use for the antiderivative. And this is really useful. It kind of gives us a shorthand because finding the antiderivatives is important. And we say this symbol means the antiderivative. This symbol means the antiderivative after you put the two numbers in and subtract them. So for example, if I want to do the integral of the square root of x, what do I mean when I do this problem? Well, what I mean is we're going to say is what is the antiderivative of x to the 1/2, and we know that this is x to the 1/2 plus 1, so that's 3/2, and then 1 divided by 3/2, which is 2/3. So you flip the denominator and do it. Let me rewrite that so it looks better. Okay, so and we also know that antiderivatives always have a plus c on it, so maybe I should write that over here. So this integral is f of x plus c. And so here's our antiderivative plus c. Okay, now if I want to do the second problem, so if I want to do the integral from 1 to 9 of x to the 1/2 dx, then what that means is that I take this equation that I just had, 2/3 x to the 3/2, and I put the numbers 1 and 9 in them. So I'll do 2/3 times 9 to the 3/2 minus 2/3 times 1 to the 3/2. And this ends up being, let's see, square 9 is 3, so this is 27. So this is 18 minus 2/3, so 17 and 2/3. Let's write it as decimal, 17.667. Maybe that's right. I don't know. 17 and 1/3, so 17.333. There we go. Okay, so you can kind of see right now the differences between the two problems, and that is that this first one, when I did this first problem, what do I do? Well, this one we just write, this one your answer is a function. So when we ask you for the antiderivative, what we're looking for is something that has an x in it, and we also have a plus c. So that's a big difference. So here we just have that a function, we stop and we circle it. Versus here, what does our answer look like? Well, here your answer is a number. And so instead of stopping with that x and instead of including the plus c, we subtract the two. And so this is where you have your function with your a and your b, going into it. Okay, so that's just a few differences between those. What I would like you to do is just try to find the antiderivatives of that next problem. So try 4.14 independently. So pause your screen right now and try 4.14. Try to do all three of those. See if you can find some success, and if you can, then good job, and we will all be very proud of you. All right. Okay, so we're done pausing our screen, and here's our first one. Our first problem is the integral of x cubed minus 3x plus 6. This is just an integral. There's no numbers on it, so we just find the antiderivative. And so the antiderivative, x cubed becomes x to the 4th with a 1/4. 3x becomes 3x squared with a 1/2. And then 6 becomes 6x. But we need one more thing. We need plus c. And so this is our answer. If I wanted to clean it up just a little bit, 1/4 x to the 4th minus 3/2 x squared plus 6x plus c. You could have circled that too. That's fine. It's not 3 and a half. It's 3 times a half. So that's important. That distinction is important. All right. Hopefully that makes a little bit of sense. Let's go to the next problem. Let's grab it. So this is the integral of secant squared. So how do I do the integral of secant squared? Well, the only way is to know, and that's to go through your derivatives. And so you start reciting your derivatives, and you go, the derivative of is secant squared, and it turns out it's the derivative of tangent of x. So the derivative of tangent is secant squared. So the integral of secant squared is tangent of x plus c. And that's all there is. So hopefully I give you, 30 problems that are just like that on the final. And you will be very pleased, because all you have to do is write that down, and you've got full credit. Hint, that's not what it's going to be like for the final. So sorry. All right, now finally we'll do the last one. The last one takes a little bit of effort. Just like previously, you can't cheat and deal with the division because antiderivatives don't work nicely in division. So we have to do a little bit of algebra. And the algebra is going to be the same algebra we've done before. And that is we unadd these things. So as you unadd them, we get the integral of x to the fourth divided by x squared is x squared. This is just 4 by itself, and this is, what if I write 2x to the negative 2? Let's not forget our dx's. It's tempting to not write those dx's down, I know, but we'll try to write them down because it's an important part of the problem, and it kind of really shows what's going on. When you get to when you get further along, you will change the letters here sometimes. In particular, you'll do some problems in multivariable calculus where you have more than one variable, and so this is going to be an indicator as to which variable is going on. But not only that, I find the dx valuable because the dx kind of tells you how to think about the problem, and that is we have a bunch of heights or values times small changes in the width. And whenever you start thinking about when do we use integrals in real problems, it's always when you have a bunch of heights and a bunch of changes in widths. So try to write that down if you can remember. All right. So what do we get? Now I'm going to take the antiderivative. X squared is going to give me 1/3 x cubed. My 4 is going to give me 4x. And then finally here I'm going to have minus 2x to the negative 1. Notice this was 2x to the negative 1 divided by negative 1, but I went ahead and changed the divided by negative 1 to just a negative sign out front, plus c. And there you go. So that's what we get. That's what we get for our answer. And hopefully you do a better job circling yours than I did. So sorry about that. All right. So a few things that I see from students. Sometimes I see students get to this part and keep. Right, so sometimes I see students get to this part and keep the integral sign. Don't keep the integral sign, get rid of it. Just like if you do the square root of 9, you don't put square root 3, you use the square root 3. The square root has already been done. You don't keep it around. Similarly with the dx, I find students write the answer and then put a dx on the end. Don't keep the dx in this end. The dx has been done. So think of these two as like your operator, just like a plus sign or a square root sign or something. But they don't act on numbers, they act on functions. And they turn this function into a new function, and it's this function, and it doesn't have an integral or a dx on it anymore. It's an equation, just like we're used to. Okay, let's talk for just a little bit before we go on about what does an integral mean? How should we think about what this integral represents in some sort of like real world terms? And the answer, there are actually a lot of ways to think about this, but I want to think about just for a moment, if we think about this f prime of x equals f of b minus f of a, well, what you can think is, what is f prime? Well, usually, if there's an f prime, that means we're talking about a rate. And so we have a rate of something occurring. A velocity is a rate, but you can also have rates of change in lots of other situations. You can be pouring water into a glass and you have a rate of change of the height of the glass, or the rate of change of the water coming out of your water hose, or the rate at which money goes into your bank account or out of your bank account. So there are lots of things in the world that have rates. And so what you find is that if you take the integral of a rate, what you get is what we call the net change. So the integral of your rate gives you the net change, and that is what is the difference between your starting amount and your ending amount. And so this is the start amount and your end amount. And so if we think of this in terms of like velocity, what would that mean? Well, it's the difference between where you ended and where you started, or how fast you traveled. So if we're thinking of velocity, this integral means we started here, and then we moved and we ended here, and so the integral is going to tell us how far we moved. So it's going to be a distance, the change in distance. If this f prime gives us something like the rate of money coming into your bank account, then this is going to be how much you ended minus how much you started with. So this is how much your bank account has increased. Hopefully it increased and didn't decrease. Hopefully you end up with a positive number when you're done here. And there's lots of other problems. So let's look at two of these and see if we can make sense of what the net change theorem might mean, or what the integral might mean in these two contexts. And I think this is valuable. It helps us kind of realize what's actually going on. So 4.15 tells us that water leaks from a tank at a rate of v of t equal to t squared minus 8t plus 16. V of t equals t squared minus 8t plus 16 gallons per hour. So let me actually give you enough space that I can put the units on here, gallons per hour. And then let's ask ourselves, for the first 4 hours, how much water leaked out in the first 2 hours? Well, what we know is that the amount of water leaked out needs to be an integral from 0 to 2. This is the change in water from time 0 to time 2. So this is going to give us that net change. So I'm going to take 0 to 2, t squared minus 8t plus 16 dt. By the way, I also want you to notice the importance of having the dt to make the units make sense, because this units are gallons per hour, but dt is in gallons. So if I think of my units, I have the units gallons per hour here. And here I have dt hours. This is the change in hours. And so when I put them together, what should my answer be? My answer should be in gallons. So I'm actually getting an amount in gallons when I think about my units. Okay, so what is this? We can do this. We just take our antiderivative, and our antiderivative is t squared, 1/3 t cubed minus 4t squared plus 16t. Hopefully you're getting good at this. Evaluated from 0 to 2. I'll put 2 in here and 0 in here. 1/3 times 2 cubed minus 4 times 2 squared plus 16 times 2 minus, and notice when I put 0 in here, I'm just going to put a big 0 because I can see it's 0, 0, and 0. Okay, so what's that answer come out to be? I'm going to have to use my, I think I could do it in my head, but man, I'm getting tired today, and it's becoming difficult. Okay, so minus plus 16 times 2. So assuming I typed all of this in my calculator correctly, I've got 18.667. So 18 2/3 is the answer. So that's how many gallons came out of our tank during those first 2 hours. If the tank started with 25 gallons, how much water is left 2 hours into it? So like this is that A part, B part. I don't know why I wrote them backwards. Sorry. How much is left? Well, if you start with 25, then we started with 25 gallons and 18.667 drained out of it. So that's going to give us our final amount. So we'll take 25 minus that answer to give us 6.33 gallons. So we have 6 1/3 gallons left. What you'll notice is that how much is left, you can have your starting amount and then subtract off the integral from 0 to 2 of that function v of t dt, and that gives us your starting a gallon minus the change in the gallons is going to give us the amount that's left over when we're done. Hopefully it makes a little bit of sense when we do this problem. Let's come over and look at 4.16 and see if we can get it to work. This would be a good time to pause your device, and this would be a good time to pause your device, read 4.16, and see if you can make sense of what the answer should be. It's a pretty simple answer, but you have to do some reading to make sense of it. All right. Hopefully you paused. Let's look at what 4.16 it says. The bacteria culture starts with 1,200. Oh, sorry, I don't want to do 1,200 organisms. The size of the colony increases at a rate of n prime of t organisms per hour. What does? Let's change that to 1,200 plus the integral from 0 to 6 times n prime of t dt. What is this going to tell us? Well, first let's think about what are the units on this thing. Well, the units here are organisms, and the units here are organisms per hour. But dt is in hours, so what you'll notice is that my units, my final answer, is going to be organisms. So this calculation is telling me the number of organisms present. Now, what about the number of organisms present? Well, this is the starting amount. And this is the change in amount. The change in the number of organisms. So what does this problem tell us? This problem tells us if you take the start amount and you take the change in organisms, then our answer is the number of organisms present after 2 hours. Was it 2 hours? 6 hours. Sorry, after 6 hours. So this problem, this is just a really fancy notation to say how many organisms are present 6 hours later. But the good thing is if you have this in terms of an equation, you could calculate in this. And this is a number you could come up with. All right. We are going to skip 4.7 here. I really like 4.17, but I'm feeling like this is a good place to end. I don't want to introduce any other kind of more complicated ideas. So 4.17 we will skip. And not only that, we're going to skip the whole next section. So section 4.5 will be skipped. I made a few small edits to the homework. The first edit to the homework is there's a typo on the bottom of the page. We're doing section 4.4, so the homework should come from 4.4. I hope you were smart enough you could have figured that out without me. But regardless, that's the homework is from 4.4. These stay the same. These stay the same, and then for that last section, just do these two problems, just 40, 47, and 49, and you don't have to do the rest of them. We're skipping section 4.5 altogether. It's a really interesting section, but you're going to review it again and revisit this in Calculus 2, and so I think I'll just let you learn it and learn it there when it'll be introduced. So I hope you're making it through the videos. I hope this stuff's making sense, and I hope you come see me because really only so much learning happens independently. A lot of it happens when you talk about this with someone else. So come see me, and look forward to getting some tests and a final exam put together. Oh, one note. I was originally planning on doing both a final quiz and a final exam, and I think I'm just going to wrap this quiz up into the final exam. So expect those to be combined together in one thing. So thanks for watching the videos, and I've really enjoyed talking to you this semester, even though things haven't gone exactly as we wished. See you soon.